In this video, I want to walk through the steps of related rates problems, and then I want to work through 4 or 5 examples in succession. It's going to be a fairly lengthy video as well, so I'll provide some indexing in the comments below the video, so you can sort of like fast forward to whatever spot you want to go into the video. All right, so here are the related rate steps. You first want to identify the known and unknown rates of change in the problem and then name them mathematically. That means name them with derivatives. You want to draw a diagram labeling the quantities that change as functions of time and those that don't change with constants. You want to write an equation relating the dependent variables, ones that are dependent on time. We'll talk about that in a minute. Take the derivative of this equation with respect to time via implicit differentiation, and then plug in known quantities of rates of change and solve for the sought-after rate of change. So in this example, we have a conical paper cup 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? Now, it's important to understand when you're doing this process that really the first 2 steps, identifying the known and unknown rates of change, and the second step of drawing the diagram and labeling the quantities can really be done interchangeably. It kind of depends on what you're more comfortable with. So in this problem, I'm going to actually draw the diagram first. I have a conical paper cup, so it's a paper cup in the shape of a cone. And it's got water in it. And you're told that the cup is being filled with water, so we get water going in, so that the water level rises at a rate of 2 centimeters per second. So as we put water in, the height of the water, which is this, is going to change, right? So the step 2 says label the quantities that change as functions of time. If you think about the height of the water, it's going to change as time changes because you're pouring water into the cup, right? So I'm going to label that as h of t because it's dependent on time. And the rate of change of that, we are told, which would be h prime of t, is 2 centimeters per second. Now, whenever you're thinking about rates of change, it's really important to think about whether they're making the quantity itself increase or decrease. And this one is when it's making it increase, so it would stay positive 2 centimeters per second. If the water were going out and the height were dropping, you would write that as a negative rate of change. So h prime, we know. Then we want to know at what rate is water being poured into the cup. Now, if you think about how you would describe that, you would say it's being poured into the cup at some sort of volume per time measurement, right? So what we're looking for is a rate of change of volume with respect to time when the water level is 8 centimeters. All right, so I've got my known and unknown rates of change. I've labeled the h of t in the diagram. Now, what are some things in the diagram, in the picture, that aren't changing as time goes by? Well, the height of the cup itself isn't changing. That's always 10 centimeters. And the radius of the cup isn't changing. This is also 10 centimeters, and clearly I did not draw this to scale, and that's fine. Now, so I've labeled the things that are changing with variables, with the actual functions of time, and the things that aren't changing with numbers. So part 3 says write an equation relating the dependent variables. So in this case, you're almost always going to be drawing upon some sort of knowledge of geometry you have. And we want something that relates the volume and the height, not their rates of change yet, because we're going to find those when we take the derivative, but the volume and the height itself. So from geometry, the volume of a cone is pi over 3 r squared h. Now, in this problem, we know rates of change of h and r and v, so we want to have those things there when we take the derivative. We don't know anything about the rate of change of the radius, so we don't want that r to hang around at all if we can avoid it. So what we can do is look at this cone from the side. We'll look at half of it. Here's the water. So we know that the height of the cone was 10 centimeters, and the radius was also 10 centimeters. And this height of the water was changing, so we labeled that h of t. Now you also know that the radius of the water is changing as well. So if I labeled that, and I know to think about radius because I'm looking again at trying to relate radius and height so I can get rid of one of them. These two are similar triangles, so I could set up a ratio that says r of t is to 10 as h of t is to 10. And that would tell me that r of t is equal to h of t. So I can actually use that up here to get rid of the h. So what I would have then is that, so v of t, and remember I wanted to have h and v, so I want to get rid of this r. So I'm going to replace the r that's here with h of t squared, and then this is also h of t. So if I were to simplify that, this would give me v of t is pi over 3 times h of t cubed. So this is the formula I'm going to implicitly differentiate. I'm going to use the chain rule for this. So when I go to take the derivative of this with respect to time, that's step 4. The derivative of v of t with respect to time is v prime of t. And the derivative of that right-hand side would require the chain rule. I bring the 3 down, multiply by pi over 3, so that would give me just pi. I reduce the power by 1, leave the inside alone, so h of t squared, and then multiply by the derivative of what's inside. That. So that's the relationship between the rates of change. So now it says plug in your known quantities and rates of change and solve for the sought after rate of change. So the thing I was looking for in this problem was v prime of t. So in order to be able to find that, I need h of t and h prime of t. And fortunately, I was given both of those things in the problem. So if I wanted v of t, at the moment I was talking about, I plug pi, I wouldn't plug pi, but pi, you'd have pi times. The h of t at the instant we're talking about was 8 centimeters. And then my h prime of t that I was given was 2 centimeters per second. So if I were to simplify that out, I believe that's 64 times 2, which is 128 times pi. And if I were to look at the units, I get centimeters squared times centimeters per second, which is centimeters cubed per second, which makes sense because that's a measure of volume with respect over comparing volume to time. So this would be the rate of change of that volume. That's how fast the water is being poured into the cup. All right, next problem. A block of ice in the shape of a right circular cone is melting in such a way that both its height and radius are decreasing at the rate of 1 centimeter per hour. How fast is the volume decreasing when R equals H equals 10? So again, I've got a right circular cone. I could draw a point up or point down. Problem doesn't tell me. I'm going to get a little picture. In this case, the entire cone is actually changing size. They tell you it's a block of ice and it's melting. So I'm going to label its height as h of t because it's changing with respect to time, and its radius as r of t because it's also changing with respect to time. When I go to look at the rates of change in the problem says how fast is the volume decreasing? So I want to know how fast the volume is changing. So what I want is v prime of t when r equals h equals 10. And what I know is that both the height and the radius are decreasing at the rate of 1 centimeter per hour. So that means that the height, h prime of t, says it's decreasing, so that rate of change is going to be negative. And the radius is also decreasing at that same rate. Like that, right? Now, in this case, the rate of change that I know that I want to find is of volume, and the rates of change that I know are of height and radius. So when I get my equation for the volume of a cone, which again is pi over 3 r squared h, I don't need to do any substitution here because I have rates of change for H and R, and I'm trying to find the rate of change for volume. So all I'm going to do is plug in the fact that these things are functions of time, and then I'm going to kick it in and start taking the derivative. So if I take the derivative of this thing with respect to time, the left-hand side would give me v prime of t. The right-hand side would require product rule and chain rule. So what I'm going to do is I'm going to treat this pi over 3 r of t squared as one thing and use the chain rule for that. So I'd bring down the 2. I'd leave the r of t alone, reduce the power by 1, so that'd be the first, multiply by the derivative of what's inside, times h of t, so that would be the derivative of the first, times the second, plus pi over 3 r of t squared times the derivative of h of t, which is h prime of t. Okay, lots of things going on here, right? So what I was trying to find was v prime of t. So I need a bunch of things here. I need r of t, I need r prime of t, I need h of t, I need h prime of t. Well, if you look at the picture, the information we were given, we have all of that. R equals h equals 10 centimeters at the instant we're talking about, and the h prime and the r prime are both negative 1 centimeter per hour. So I'll plug all that in. 2 pi over 3 times r of t, which at this moment is 10 centimeters, times r prime of t, which is negative 1 centimeter per second, times h of t, which is 10 centimeters, plus pi over 3 times r of t squared, so that would be 10 centimeters squared, times h prime of t, which is negative 1 centimeter per hour. So when I go to simplify this, let's see, that would be 100 times 2 is 200 times negative, so that's negative 200 pi over 3 for this first thing before the addition, and the units would be cubic centimeters per second, plus for that second thing, 10 squared is 100 times negative 1 is negative 100, so negative 100 pi over 3, and the units on that will come out as centimeters cubed per hour as well. So when I put those two together, you get negative 300 pi over 3, which is negative 100 pi cubic centimeters per hour. And I'm pretty sure this should have been hours there. All right. The next example says that in a right triangle, leg x is increasing at the rate of 2 meters per second, while leg y is decreasing, so that the area of the triangle is always equal to 6 square meters. How fast is the hypotenuse z changing when x is 3 meters? So again, steps 1 and 2, interchangeable. I can identify the known and unknown rates of change, name them mathematically, draw a diagram, label changing quantities. So I'm going to start by drawing my diagram. I have a right triangle. Poorly drawn. And it says leg x is increasing at a rate of 2 meters per second. So I have a leg that's increasing. So we're going to call that a variable, x. And its rate of change with respect to time is 2 meters per second. Now that's positive because it's increasing. And it says that leg y, so there's a variable. By the way, both of these are variables in terms of time. Leg y is decreasing so that the area of the triangle is always equal to 6 meters. So we know that this is decreasing at some way such that the area of the triangle is always equal to 6 meters. Now, we can't write a direct statement for this, so I'm going to say such that area is constantly 6 square meters. And we'll come back to that in a moment. How fast is the hypotenuse z changing? Z of t. So what is z prime, or dz dt, when x is 3 meters? And that's what we're looking for. Okay, so we know we've got 3 sides of a right triangle, and at some point we're going to involve the Pythagorean theorem. So I can go ahead and write that out, because this is the equation that relates those dependent variables. But when we go to look at sort of the rates of change that we want to plug in, we're going to need a little more information. I'm going to go ahead and come back to that in a moment. When I go to implicitly differentiate this thing, I would use the chain rule for each of those terms. And strange little mark there. The derivative would come out as 2 times x of t times x prime of t, 2 times y of t times y prime of t, and 2 times z of t times z prime of t. Now keep in mind in this problem, because we have information about 3 different rates of change, we actually didn't need to substitute anything because we're going to need all those rates of change in the equation that we have. So right now, what I'm looking for is dz dt, which is this z prime of t right here. So I'm going to need information about everything else in the problem to be able to solve it. And really, what I'm given is this 2 meters per second for dx dt. So I need to find information about x, y, and y prime. Oh, I've already got x, right? Because I'm told that x is 3 meters, and I'm told that dx dt is 2 meters per second. So this term, I can go ahead and fill out. Let's see, 2 times 3 meters times the x prime, which is 2 meters per second, plus 2y of t, which I don't know right now. Don't know y prime of t yet. Don't know z yet. And I'm looking for that z prime. Now, I'll work on simplifying that more in a couple of minutes. But I'm going to need to do something about this dy dt. So I'm told that the area is constantly 6 meters squared. So you know the area of a triangle, especially in this one, would be 1/2 base times height. And that's 1/2 x of t times y of t. And we're told that that is constantly 6 square meters. So I can use that to actually get a relationship between x and y. And since I know information about x at the instant that I have and dx dt at the instant that I have, I can use that to get y and y prime. So this is what that's going to look like. I've got x of t times y of t equals 12. And if I were to look at the instant that I have, where x is 3 meters, if I plug that in here, then I can find that at that instant, my y of t is 4. So I'm going to go ahead and stick that in here. Left my 2 off. Now, I also need to find dy dt, which means I need to find a rate of change that involves y, and it involves some sort of rate of change that I know. And the only rate of change that I know besides that not besides that, the only rate of change that I know, period, is the dx dt. So what I'm going to do then is take the relationship that I have, between the x and the y here, and I'm going to take the derivative of it with respect to t. This will give me a relationship between dx dt and dy dt. So this is a product rule. So let me bring this down here. So it's first times the derivative of the second plus second times the derivative of the first equals the derivative of 12, which would be 0. Now, I don't want to take the derivative of this thing where I plugged in the 3, because that 3 is a quantity that's changing. It's like an instantaneous measure. So if it's changing in the problem, you never want to plug it in before you take the derivative, because then the derivative assumes that it's constant through the problem. So I've got this relationship now between x, y, dy dt, and dx dt. So I'm going to plug in stuff that I know. So the instant that I care about, x of t is 3 meters. Y prime of t is what we're trying to find in this case. Y of t is 4, we just found that, and dx dt was 2 meters per second. So now if I go to solve y prime of t, I will actually get a number, and if I'm not mistaken, what I get is negative 8/3. And you get meters per second because you get meters squared per second divided by meters. So now that will go here. I can fill in the rest of this. So 2 times 3 times 2 is 12. And then I need z. Well, if you look at my instantaneous measurements that I have, y was 4, x was 3. I could use Pythagorean theorem. It's a Pythagorean triple, so no big deal. It ends up being 5 at this instant that we're talking about. And now it's just a matter of doing the arithmetic. So this is 12 meters per second plus, it's going to be a negative, so negative 64/3, I believe, equals, and this would be squared because we multiply the meters squared out. This would also would have been squared. Mess my units up there. So this would be 10 meters times z prime of t. If I combine these two things, let's see, that's 36, 64, that's 24, and 28. So negative 28/3. And when I divide both sides by that 10, we get negative 28/30, which is negative 14/15. And when you divide the units, you get meters per second. And that would be z prime of t at the instant. Right. Next example. Girl is flying a kite on a string. The kite is 120 feet above the ground, and the wind is blowing the kite horizontally away from her at 6 feet per second. At what rate must she let out the string when 130 feet of string has been let out? So here again, we have another right triangle problem. I'm going to draw my picture. Here's the kite. Here's the girl. Interesting drawing. So it says the kite is 120 feet above the ground and wind is blowing the kite horizontally. So that means that 120 feet height is constant in the problem. If the kite's being blown horizontally, it's not going up or down. So I'm going to go ahead and label that in the picture with a constant. The wind is blowing the kite horizontally away from her at 6 feet per second. So if it's moving that way, then that rate of change is going to affect this length here, which means it's a variable. And that variable's rate of change, I'll switch back to the to the Newton notation this time, would be 6 feet per second. And it's increasing, so we may keep it positive. At what rate must she let out the string? So the string is the hypotenuse of this triangle, right? So let's call that S of t for string. And we want to know at what rate must she let it out. So S prime of t is what we're looking for when 130 feet of string has been let out. So when S is 130 feet. Now, this problem, compared to the last one we had, was actually much easier. So I have rates of change for X and S. I want some sort of relationship between X and S. Clearly, sides in a right triangle along with the 120. So that's a Pythagorean theorem question. So when I write Pythagorean theorem, I don't need to do any substitution because all the variables I have here have associated rates of change that I either want to find or I want to, are given to me in the problem. So I'm going to take the derivative by implicit differentiation. And I'm going to plug in what I know. Now the thing I'm trying to find is S prime. So I need X, I need X prime, I need S. So I'm given directly in the problem that X prime is 6 feet per second. I'm not given X directly, so we're going to come back to that. I'm given S of t directly at the instant at which I care, and I'm trying to find S prime. So now all I really need to do is figure out what X is, and I can do that by looking at my original relationship, which is that Pythagorean theorem, and the instantaneous information that I have, which is 130 feet. So if I were to take X of t, square it, add that to 120 squared, that should equal 130 squared. So let's see, this is 169 with 2 zeros. This is 144 with 2 zeros. So if I subtracted that from both sides, I believe that would give me 2,500. Ooh, that's messy, sorry. So X of t then would be 50. And that's what's going to go here. So I'm going to finish solving it, basically. Let's see, this would be 260 feet times S prime. And that would be 12 times 50, which is 600 feet squared per second. So when I divide both sides by 260, that would be 60 over 26, which is 30 over 13 feet per second. All right, one more example. A right circular cylinder of constant volume is being flattened. At the moment when its radius is 3 centimeters, the height is 4 centimeters, and the height is decreased at the rate of 0.2 centimeters per second. At that moment, what's the rate of change of the radius? Okay, so we got a right circular cylinder. The volume is constant, so it's not going to have a rate of change. At the moment when its radius is 3 centimeters, now think about this for a second. If the cylinder is being flattened and the volume is staying constant, the height's going to be changing and the radius is going to be changing in order to maintain that constant volume. So I'm going to go ahead and label those with variables. R of t for the radius, h of t for the height. Now, we're told at the moment when its radius is 3 centimeters, the height is 4 centimeters, and the height is decreased at the rate of 0.2 of a centimeter per second. So we know h prime of t is negative 0.2 of a centimeter per second, negative because it's decreasing. We're asked to find the rate of change of the radius, so we want to know what r prime of t is at this instant, and that instant is when the radius is 3 and the height is 4. Like that. So I've got rates of change. I need some way of relating them. So I've got volume of a cylinder is equal to pi r squared h, which are both functions of time. Now, here's the thing. In this problem, the volume, you're told, is constant, so it's actually not changing. So it doesn't matter what time you're looking at this. That v is a number. So what I'm going to say, I'm going to go ahead and find what that number is. So my volume is constant. And you're told that the radius is 3 and the height is 4 at some instant. So my volume is pi r squared h. Oops, that's supposed to be a 4, not an h. So this is 36 pi. So when I plug this into the equation, and I'm trying to write the relationship here, instead of leaving that as a v, because it's constant, I'm going to replace it with the constant. Now r is a function of time, so I'll rewrite that, and h is a function of time as well. I'm going to do a little simplification, except I'm going to write that a little more clearly. And this is a relationship between r and h. Now I'm ready to implicitly differentiate. Now this, I could separate the two things by dividing both sides by, say, h of t, or by rt squared if you wanted to. I'm just going to do it the way it is. I don't mind doing the product rule with the chain rule inside of it. So I'm going to take the derivative of both sides. Derivative of 36 is, let me go ahead and write that. Derivative of 36 is 0. And then for this product rule, to take the derivative of RT, I need to use the chain rule. So that would look like this. Times h of t plus r of t squared times the derivative of h of t, which would look like that. And again, if you need to write out all this to sort of keep the rules straight, perfectly fine. So the thing I'm asked to find in the problem is r prime of t, which is right here, which means I need information about everything else. So let's look. I've got h prime of t I've got r at the instant that I want. Oops, no square on that one. I've got h at the instant I care about. And that looks like all the variables that I needed. So let's bring down everything that we had here. Yeah, looks good. So now all I have to do is solve for r prime. So let's see, this would be 24 centimeters squared times r prime of t. This would be -6/10 centimeters cubed per second. So if I move the 0.6 to the other side and divide it by 24, if you did the math on that, I'm pretty sure you'd get 1/40. And the centimeters cubed per second divided by centimeters squared would give me centimeters per second. I'm just going to double check my math real quick, make sure that makes sense. That would be 6 divided by 240. Yep, 1/40. So that is what we were looking for.